Hello, and today we're going to be going over Exam 1 review. And I'll be trying to give you some tips and tricks on how to do the exam and maximize your effort. So, the first thing we're going to do is we'll look at question number 1. Train tracks rails are often joined through a chemical process called thermite welding, where a mixture of powdered aluminum and iron oxide are mixed into a crucible, ignited, and then molten iron formed is leaked into the junction between rails. All right, part A. Give the oxidation numbers for each instance of each element in the thermite reaction. So if we're doing the oxidation numbers, again, you want to look at the bottom of your useful equations packet on the bottom of page 1. And we'll see that almost always oxygen is going to be a -2. So we'll just put -2 there. Then we need to figure out what it is for iron. And the easiest way to go about doing this is we can say we have -2 times 3. That's for the oxygens. We're going to add that to our iron. We don't know what iron is, so we'll just say it's X, 2X, and all that is going to be equal to the charge. Now, for this particular molecule, there's nothing written there, so the charge is neutral or 0. All right. So now we have -2 times 3 gives us -6. So we'll have 2x minus 6 is equal to 0. We can say 2x is equal to +6. Bring it to the other side, and then we can divide both sides by 2. We'll get x is equal to 3. So for the iron, each iron is going to be a +3. So again, for oxidation numbers, you want to keep in mind that it's for the average of that particular element in the compound. And so we should get a +3 for iron and -2 for oxygen. Then we can move on to the next one. Aluminum is in its elemental form. So if you have anything that's elemental form with no charge, that's always going to be 0. Then we have the same thing over here for iron. So it's elemental form, so that one's going to be 0. And then we get back to another compound. This time we need to figure it out. And almost always, whenever you have oxygen, that is going to be a -2. The only cases where it's not is if it is in its elemental form, so it's just O2 by itself, or it's in a peroxide. And I'm not going to test you guys on peroxide because, they're not all that common. All right, so now we can do the same thing for over here. We can have our -2 for each of the oxygens multiplied by 3, giving us a -6. And all that needs to be equal to 0. So in order to counteract that, we need all of our aluminums to be equal to +6. And so we can divide that by 2 for each aluminum, and we'll get a +3. All right, so now we figured out all the oxidation numbers. For grading purposes, just so you know, in this case, each of the oxidation numbers are each worth 1 point. And so this would be a total of 6 points. Now we need to go ahead and try to balance the equation. And for balancing the equation, we're going to, again, just look at the products and reactants. So I normally draw a line here. We'll have our reactants over here, our products over here. And you want to go element by element. So we'll look at iron first. All right, on the reactant side, we have a 2 subscript here, meaning that we have 2 irons. So we'll just say we have 2 there. And then on the product side, we don't have any subscripts here, so this is just iron by itself. So that's going to just be 1 iron. Now, in order to make this be 2 so they can be equal, we're going to put a coefficient in front of the iron of 2, and now we have 2 irons on the product side. Then we can look at oxygen. For oxygen, we have a 3 subscript here, so we have 3 oxygens in total here. Again, this coefficient is not written, so let's assume to do 1. So we'll have 1 times 3, giving us 3 oxygens. If we look at the product side, we have a similar scenario here, where we have 3 subscript there and a 1 coefficient. So we're going to have 3 oxygens currently. Now we want to look at the aluminum. Now for the aluminum, we have only 1 on the reactant side. So we're going to put 1 there. And then on the product side, we have a 2 subscript and this 1 coefficient. So this will be 1 times 2, giving us 2 aluminums. And now to make these equal, we need to put a 2 coefficient in front of the aluminum. And then that will allow us to go ahead and make that 2. So now we have all of our elements equal on both the reactants and product side. And now we can go ahead and move on with the rest of the questions. So for balancing, that'll be worth 2 points for the entire balancing. So if you ever find yourself in a situation where you are struggling with balancing it, and you get on the exam and you are really freaking out, one thing you can do, just so you can prove your knowledge in other areas, is you can just simply say, all right, well, I'm going to say this is a 1, 2, 3, and 4, and then solve for the rest of the question. You can always come back to this question later. Let's say you get done with everything else on the exam, you decide to come back and you try to balance it out, and then when you go and balance it, you'll find that, all right, well, this one was actually a 2, so maybe I don't have to change anything for aluminum if that's what I was using. But if you need to use the iron, or say the iron oxide or the aluminum oxide, you can make those changes accordingly, and you'll have just a little bit of numbers to change and then a little bit to redo on your calculations. But again, if you're setting up the railroad cross method, this should be a fairly quick process. So if you're struggling with balancing the equations, I highly recommend, all right, well, just skip it for the time being. Show me what you know, and I'm going to award you points for what you're able to show me for what you know. All right. Moving on to the rest of the exam, we're supposed to write the reduction half reaction. So for the reduction half reaction, what we're going to do is we need to find out which oxidation numbers are changing. So in order to do that, let's go ahead and remove this so I have a little bit more space. All right. For the reduction half reaction, we need to look for the oxidation number decreasing. But first, you may want to just find which ones are actually changing. So we have the iron going from positive 3 to 0. We have the aluminum going from a 0 to a positive 3. So for the aluminum, since we're going from 0 to positive 3, the oxidation number is increasing. And whenever the oxidation number increases, this is considered oxidation. And then whenever we have the oxidation number decreasing, such as for iron, we're going from positive 3 to a 0. If it's ever decreasing or being reduced, this is reduction. So once you figure out what is being reduced, all you have to do is write down what your reactant is and what your product is. So what we're going to do is we're going to write down our iron, and then we can look at our oxidation number. We have our oxidation number of positive 3, so that's going to be a 3 plus. And then we're going to write down whatever our product was. In this case, it's going to be iron, and it has a 0 oxidation number, so it's going to be neutral. All right, so we'll just write iron neutral. Now we need to determine where our electrons need to be. So in order to do that, we want to make sure the charge of everything on the reactant side is equal to that of everything on the product side for our half reaction. So over on the reactant side, we have a positive 3, so we have 3 plus. And over on the product side, we have neutral, so it's 0. So we need to add electrons in order for both sides to be equal. Since we have a higher positive value on the reactant side, I'm going to add 3 electrons to the reactant side. So now this is going to be a positive 3 plus 3 times negative 1 for negative 3 overall for this. And for everything in the reactant side, we're going to have positive 3 plus the negative 3, negative is 0. And that's going to match up with what we have on the product side of just 0. So that's our reduction half reaction. Another thing you can do to help yourself out if you need to, if you're having trouble remembering which one's reduction, which one's oxidation, is you can go and look in your useful equation packet, and it should be on the back of the second page, or page 4 if you're just using the electronic version, and you can look at the reduction potentials. Those reduction potentials are all written as reduction reactions. And if you forget that, it says it on the bottom little caption there when it's describing it. All right, so now we got that part done, and that was worth 5 points. And now we'll move on to part C. All right, so for part C, we have you perform this reaction by mixing 2.134 grams of iron oxide with excess aluminum. Determine the grams of pure iron. So what we're going to do is we want to look at what we're given. So we see that we have 2.134 grams of iron oxide. So that's what we're going to start with. And then we're trying to figure out how many grams of iron are produced. And so that's where we're trying to get to. So I'm going to start off with the variable that we're given, this 2.134 grams of iron 2 oxide. All right, now we need to be working towards getting to moles because we're trying to convert from one substance to another substance. And one thing we can use for this is we can use our periodic table. So if we look at our periodic table, we can determine that we have the molar mass where we can add in 2 irons, so 55.85 times 2, plus our amount of oxygen, so 16.00 times 3, and you take the sum of all of that, and we can get our molar mass. If you do that, you'll determine that the molar mass is 159.7, and that'll be grams of iron 2 oxide. And that is going to be equal to 1 mole of iron 2 oxide. And I highly recommend you to, every time you calculate molar mass, just do it for 1 mole. That'll make it a lot easier for you to avoid making any kind of mistakes or calculation mistakes later on. And so looking at this, we can see we have grams of iron oxide on top, grams of iron oxide on bottom. So these will cancel out. And we're left with moles of iron oxide on top. So now we're in moles. We can go ahead and look at our chemical equation. We can see that for every 1 mole of iron oxide, we make 2 moles of iron. So we're going to just use these coefficients. There's nothing written down here, but this is considered to be a 1. So we're going to have a 1 moles of iron oxide are equal to 2 moles of iron. So that's simply what we're going to write down. To figure out which side goes on which, we're looking at moles of iron oxide up here, so we need to have that on bottom. So we're going to say 1 mole of iron oxide on bottom is equal to 2 moles of iron. Now that we're in our desired compound, now we need to convert to our desired units. So now we need to convert to grams of pure iron. And again, for this, we'll just use our periodic table. And when we look at iron, we see that it's 1 mole of iron, put that on the bottom, is equal to 55.85 grams of iron. All right, at this point, we want to double check all of our units, make sure that we have the desired species. So our grams of iron oxide on top, grams of iron oxide on bottom, those cancel out. Moles of iron oxide on top, moles of iron oxide on bottom, those cancel out. Moles of iron on top, moles of iron on bottom, those cancel out. And now we have grams of iron on top, and there's nothing to cancel out, and so that's our units, grams of iron, and that's actually what we're looking for. So we did it right. So now what we want to do is we want to multiply all the numbers on top. So it's 2.134 multiplied by 2, multiplied by 55.85, and then divide by everything on bottom. We're going to divide that by 159.7. So if we do all those calculations, we should get 1.49259737 grams of iron. If we want to go back and check our significant figures, we have 1, 2, 3, 4. And on the next number, we have 1, 2, 3, 4, 5. This is an exact equality, so that's not going to limit our significant figures. And if we look at the last number here, we have 1, 2, 3, 4. 4 sig figs. So we have 4 sig figs, 5 sig figs, and 4 sig figs. When you do multiplication and division, you're limited to the lowest number of significant figures. So in this case, 4. So we are going to count 1, 2, 3, 4. We're good down to that 2. So we're saying we're good down to that 2. We're going to say 1.49. And since the number to the right of that 2 is greater than 5, we're going to round that up, and it's going to become a 3. So I have grams of iron. So that's our answer. And normally it's a good idea to go ahead and box your answers if you're writing on your notes, so it's really easy to see where that is. All right, so that's essentially how we do problem number 1. I'll be going through the rest of the problems a little bit faster. I forgot to tell you about the points. So the points for this last step was worth 10 points. Essentially, we have 2 points for each conversion, and then we have 2 points for determining the significant figures. All right, so now let's go ahead and we'll move on to question number 2. And give me just a second to copy that over. All right, so for question number 2, it reads, in 1918, Fritz Haber won the Nobel Prize in chemistry for inventing the Haber-Bosch process. This process used high pressure, 200 bar, and high temperature, 500 C, to synthesize ammonia from its elements. Determine how many grams of ammonia, NH3, are produced if 0.989 liters of N2 are mixed with 2.613 liters of hydrogen gas. And then we're given some conversions, some extra information. Density of gases at 200 bar and 500 degrees Celsius for N2 is 87.218 kilograms per cubic meter, and hydrogen gas is 6.2696 kilograms per cubic meter. 1 kilogram is equal to 1,000 grams, and 1 cubic meter is equal to 1,000 liters. And the other extra bit I added on here was the periodic table. This is just so we can, use this simply for calculating molar masses. So the first thing we want to do is balance our equation. When we do that, again, we can kind of divide this into 2 parts. We'll say reactants, products. So looking at nitrogen, we have 2 in our reactant side, and we only have 1 in our product side. So we're going to have to put a coefficient in front of the NH3. That'll make it 2 nitrogens. This did change the number of hydrogens as well, but since we have balanced hydrogens yet, we don't have to worry about doing anything because of it. When we look at hydrogens, we have 2 on the reactant side, and on the product side, we have 2 for our coefficient here. We need to do 2 times this subscript 3. So we have 3 H3s, or 3 hydrogens for every NH3, and we also have 2 of those, so we need to multiply those together, so we'll have 6. So in order for us to get 6 hydrogens on the reactant side, I'm going to need to put a coefficient of 3 in front of the H2. And now this changes our number of hydrogens to 6 for both sides. All right, so now that we have our equation balanced, we can go ahead and start trying to solve for this. We need to determine how many grams of ammonia are produced if 0.989 liters of N2 are mixed with 2.63 liters of hydrogen. So we're looking at this. Our starting stuff is this 0.989 liters of nitrogen and 2.613 liters of H2. So we have 2 starting, 2 reactants, 2 amounts for our reactants. So when we're trying to figure out how much NH3 we have, and we'll go ahead and highlight the grams of ammonia, or grams of NH3. All right, when we're trying to determine the amount of ammonia we have all the information we need to do it for hydrogen, and we have all the information we need to do it for nitrogen. So since we have essentially 2 reactants, or 2 quantities for our reactants, we know this is going to be a limiting reactant problem, meaning we need to essentially solve this problem twice. So that's what we're going to do. So we're going to do one with nitrogen, and then we'll do another one with hydrogen. So looking at the nitrogen, we're going to start off with what we began with. And so we're going to have 0.989 liters of nitrogen. All right, now we need to find something else that has liters of nitrogen. Liters of N2. And when we look at our problem, we don't see anything with liters of nitrogen. So we do have something that has liters to cubic meters. And so I'd say let's go ahead and try to go with that. And eventually we're going to work towards where we have nitrogen where we can go from cubic meters to kilograms. So using that little bit of extra information, we see that we have 1,000 liters of N2 for every 1 cubic meter of N2. All right, now we need cubic meters of N2 on bottom. And I alluded to this earlier, but now we can use the density right here. So we're going to say for every cubic meter of nitrogen, or N2, we have 87.218 kilograms of N2. And so whenever you have a fraction like this, remember that number is going to be associated with the unit that is on top. All right, and so we're going to just break that up into a fraction. And so we can see for every 1 cubic meter of N2, we have 87.218 kilograms of N2. All right, now we're working towards trying to get to moles. Now, one thing that we can remember is we can always use molar mass. And if we look at our periodic table, we can see that nitrogen, so over here, has 14.01. So if we have 2 nitrogens, that'd be 28.02. Now that's going to be units of grams per mole. And we don't have grams of N2 yet. We have kilograms. And so we're going to have to do another conversion where we say that 1 kilogram of N2 is equal to 1,000 grams of N2. And again, you can use the backside of the first page of your useful equations packet, or second page if you're looking at electronically. Or you can just memorize that, kilo means 1,000. So if you have a kilogram, that's 1,000 grams. All right, so now that we're in grams of N2, we can use our molar mass, getting that from the periodic table, and we say that we have 28.02 grams of N2. So again, that's just 14.01 times 2 is equal to 1 mole of N2. All right. Now that we have moles, we can use our chemical reaction. So we can see that for every 1 mole of N2, we make 2 moles of NH3, or ammonia. So now we're going to say for every 1 mole of N2, we make 2 moles of ammonia, NH3. All right. Now our question was asking us for grams of ammonia produced, or grams of NH3. So we have one last step to go from moles of NH3. So we're going to say for every 1 mole of NH3, we can use our periodic table, and we can add together nitrogen at 14.01, and then hydrogen, which is in the upper left corner here. We have 3 of those, so we'll do 1.008 multiplied by 3, and we add all that up together, and we get 17.034 grams of NH3. That number is going to be limited to the 3 for significant figures because we're adding together 14.01 and 3.024. So the nitrogen is going to be limiting us to the hundredths place. For addition, you're limited to the decimal place, so the least precise decimal. In that case, the hundredths decimal place. All right, so now we can double check our units. We have liters of N2, cancel out with liters of N2, cubic meters of N2, cancel out with cubic meters of N2, kilograms of N2, cancel out with kilograms of N2, grams of N2, canceling out with grams of N2, moles of N2, canceling out with moles of N2, and then we have moles of NH3, canceling out with moles of NH3, and then we're left with grams of NH3. So we are in the correct units. Now we need to double check to make now we're going to multiply everything on top. So 0.989 multiplied by 87.28 or 218, multiplied by 1,000, multiplied by 2, and then multiplied by 17.034. And then we're going to divide by everything on bottom. We're going to divide by 1,000, and then we're going to divide by 28.02. And if we do all that math, highly recommend you using calculator. If we do all that math, we're going to get 105. All right, we're going to have 105 grams of NH3. All right, sorry for truncating it. I worked this out earlier, but the last numbers are blurry. So looking at sig figs, we have 3 sig figs here. Essentially going 1, 2, 3. This 0 is just a placeholder, so it doesn't count. For this number, we have 5 sig figs. For this number, we have 4 significant figures. And then for the last number, we have 4 significant figures. So since we have 3, 5, 4, and 4 for significant figures, we're limited to the lowest one. So that would be 3 significant figures. So that's why it's 105 grams. All right, but we're not done yet. So what we need to do is we need to solve it this time for hydrogen. So this time we're going to use our hydrogen starting values. So we saw that we had, the question read that we had 2.613 liters of H2. And we're going to follow a similar process again. We need something that has liters of H2. And the only thing that we can see is that we have this liters right here where we have 1,000 liters is equal to 1 cubic meter. So it's going to be a very similar process. We're going to have 1,000 liters of H2 for every 1 cubic meter of H2. Now I need to find something with cubic meters of H2. And now we're going to be looking at the density of H2. So over here we can see we have cubic meters of H2, and that's going to be equal to 6.2696 kilograms of H2. So let's go ahead and write that down on here. We have 1 cubic meter of H2 for every 6.2696 kilograms of H2. Now we need to go from kilograms to grams. So let's say for every 1 kilogram of hydrogen gas, or H2, that is 1,000 grams of H2, or hydrogen gas. Then we can look at our periodic table, and we already did this once earlier, but looking over in the top left corner, we have this 1.008. So if we multiply that by 2, since we have 2 hydrogens, we're going to get 2.016 grams of hydrogen, or grams of H2, for every 1 mole of hydrogen gas, or H2. Now that we're in moles, we can use our chemical equation. And so when we look at our chemical equation, the coefficient in front of the H2 is a 3. So we're going to say 3 moles of H2 for every 2 moles of ammonia. So we got 3 moles of H2 on bottom, so our units cancel out, for every 2 moles of NH3. Now the last part of this is the exact same as the previous working out, where we can say for every 1 mole of NH3, that'd be 17.034 grams of NH3. All right, we can double check all of our units, make sure everything cancels out that needs to cancel out. So we have liters of H2 on top, liters of H2 on bottom. So those are going to cancel out. Cubic meters of H2, cubic meters of H2, kilograms of H2, kilograms of H2, grams of H2, grams of H2, moles of H2, moles of H2. And then I forgot to write down moles on there. Let me write down moles. Moles of NH3, canceling out with moles of NH3. And then we're left with grams of NH3. All right, so now we need to multiply everything on top. We're going to multiply that 2.613 by 6.2696 by 1,000 by 2, and then by 17.034. Then we can divide by everything on bottom. We'll divide by 1,000. We'll divide by 2.016 and divide by 3. And if we punch all that in our calculator, we'll get 92.281.384 grams of NH3. And looking at our significant figures, we should be limited to 4 significant figures, mostly because we have 4 significant figures here, we have 5 here, we have 4 here, and then our last number also has 4 significant figures. Oh, I'm sorry, it has 5 significant figures. No, it's just 4, sorry. I didn't underline the 3. All right, it has 4 significant figures. So we're going to be limited to this 8 right here. So if we write that out again, we have 92.28 grams of NH3. Now what we need to do is we need to compare these two numbers. So I'm going to rewrite that again. We'll do this in black. So we have 92.28 grams of NH3. And we're going to compare that with our 105 grams of NH3. We need to determine if it's less than, equal to, or greater than. And since 92.28 is less than 105, we are going to choose the lesser of the two. And so our answer is going to be 92.28 grams of NH3. And the real reason for all that is, as we're making this, we will eventually run out of hydrogen gas, our H2, after we've made 92.28 grams of NH3. Once we run out of H2, the reaction cannot go on anymore, so we can't go on to make the 105 grams of NH3 coming from the nitrogen, because we ran out of hydrogen. So in this case, we have 92.28 grams of NH3 being produced, and hydrogen is going to be our limiting reactant. All right, well, hopefully that's making some sense. This particular question is worth 27 points. Essentially, you had roughly 2 points for each conversion. So we had 14 points for the top section, and then for the bottom section, that's worth 8 points because part of it was essentially repeating. So just this last section was repeating, so that wasn't worth any value. Then we also had 2 points for deciding which was our limiting reactant, or determining which amount was the correct one. And then 2 points for significant figures, and then also a point for balancing. All right, so let's go ahead and move on to question number 3. And give me just a second to pull that one up. All right, so question number 3. The biological process of cellular respiration is a reduction-oxidation reaction, or redox reaction, where glucose is combusted to create carbon dioxide and water. You drink a 240.1 milliliter can of Coca-Cola, which contains sugar, or glucose, C6H12O6. The concentration of the sugar in the Coke is 0.9020 molar of C6H12O6. Then we're given a chemical equation, and we can go ahead and balance that. Let's go ahead and balance that. So try and balance this one. We want to make sure everything on our reactants and products are the same. I don't actually have a lot of space here, so I'm going to just go ahead and do it on the bottom. All right, we got reactants and products. So we're going to look at carbons first. And there might be better methods than just going down the line as far as all your elements are concerned, but I just want to show you that this process can work. So we have 6 carbons coming from the subscript 6 here. And then looking at our products, we only have 1 carbon. So in order to make those equal, we're going to put a coefficient of 6 in front of the CO2. Once we do that, that's going to make our carbons the same. Now this would change our amount of oxygens, but since we haven't balanced oxygens yet, we don't have to worry about it. Then we can do hydrogens. For the hydrogens, we can see that we have 12 hydrogens from this subscript here for our reactant side. So put down 12 there. And then looking on our product side, we have 2 hydrogens because we have 1 subscript or 1 coefficient here and a 2 subscript there. So 1 times 2 is 2. Now to make that go up to 12, if I put a 6 coefficient there, we'll have 6 times 2, and now that is equal to 12. And so we'll have 12 hydrogens on each. And again, this would change the number of oxygens on our product side, but since we haven't balanced oxygens yet, we don't have to worry about it. Then we can look at oxygens finally. And if we look at on our reactant side, we have 2 times 1. So this is only going to be 2 oxygens. Plus the 6 subscript here. So this 2 is really an 8. I'll go ahead and rewrite that. All right, so we really have 8 oxygens there. And let's go ahead and erase that as well. All right, so now we need to look at our product side. For our product side, we have 2 times our coefficient here, 6. So that would give us 12. But we also have oxygen over here. So we have nothing written there, so that's a 1. Times 6, so 6 times 1 is 6. So now this would become actually 18. So we can make that 18, but I'll go ahead and rewrite it so it's a little bit nicer. All right, so we need 18 oxygens on the reactant side. We only have 8. So now we need to figure out what we need to multiply this O2 by. If we try to multiply the sugar, or the glucose, this would change our number of carbons and hydrogens, and we have to go back and rebalance all of these. But if we do it for just this lone individual oxygen, it's only going to be adjusting this element. This will make the process a lot easier. So we're going to just do that. It's actually the only way to go about doing this. So if we multiply this by 6, we'll have our 6 oxygens from the sugar, and then we'll have 6 times 2 coming from the oxygen. So now that will become 6 plus 12, which gives us 18. So then we'll be up to 18 on our reactant side. So we have 6 carbons on the reactant side, 6 carbons on the product side. We have 12 hydrogens on the reactant side, and we have 12 hydrogens on the product side, 18 oxygens on the reactant side, 18 oxygens on the product side. So now all the elements are equal between the reactants and products, and so the thing is balanced. All right, let's continue on with reading the question. An average human inhalation breath contains 18.135 milligrams of oxygen. So for each breath, that contains 18.135 milligrams of oxygen. Assuming that all the oxygen inhaled will be used for the purpose of this chemical reaction, determine how many breaths must be taken to inhale enough O2 to react with all the glucose. All right, so looking at the question, we see that we drank 240 milliliters of a Coke. All right, and that Coke has a concentration of 0.902 molar of glucose for that solution. The other bit that we know is that each breath contains 18.135 grams of oxygen. So our starting thing is still going to be this amount of Coke that we drank, and we're trying to determine how many breaths must be taken of O2 to get enough O2. So the way I'm going to start this out is I'm going to start off with our variable, like we normally do. And so I'm going to write down 240.1 milliliters of our solution. So if you want, you could just write Coke or solution 1. I'm going to go ahead and write down the concentration because that's what I'm used to doing. 0.9020 molar, and then this is glucose, so C6H12O6. All right, now our goal is to get to moles. So in order to do that, we need to remember that when we're looking at this capital M for the concentration of our Coca-Cola, capital M, that's going to be moles over liters. So moles of your analyte or moles of your substance divided by liters of your solution. So another way of actually reading this number is this is going to be 0.902 moles of C6H12O6 for every 1 liter of our solution, or 1 liter of Coke. All right. So now what we need to do is we're going to plug. So we need to get to liters, and we have milliliters. So now we need to plug in a conversion to go from milliliters to liters. So there's 1,000 milliliters for every liter. So I'm going to go ahead and put our solution here. 1,000 milliliters of our 0.9020 molar C6H12O6 solution is 1 liter of our 0.9020 molar C6H12O6. And again, you can put whatever label you want in there for your solution. You can say Coke, you can say solution 1, whatever you want. So now that we're in liters of our solution, we can now use our molarity. So we're going to say for every 1 liter of our solution of 0.9020 molar C6H12O6, that's going to be equal to 0.9020 molar, or sorry, not moles, it's going to be moles, not molar, moles of C6H12O6. Now that we're finally in moles, we can use our chemical equation. Now, a lot of times, I've seen students get a little confused at that point, and they're like, well, we never used our molar mass. You don't have to use molar mass. That's kind of one of the beauties of using molarity. You don't have to use molar mass. You're just trying to get it to moles, and now we are moles of glucose, so we can say for every 1 mole of glucose, we make 6 moles of oxygen, or we require 6 moles of oxygen. And so in order to figure out the amount of oxygen that we're going to need, eventually figuring out how many breaths we need, we're going to say for every 1 mole of C6H12O6, we're going to be needing 6 moles of O2. All right. Now that we're in moles of O2, the conversion that we had that has O2 in it has milligrams. Well, in order to go from moles to milligrams, we can look at our periodic table and we can go from grams to moles, and then we can use another conversion to go from grams to milligrams. So for O2, it's 16.00 grams per mole, since we have 2 oxygens per O2 molecule. This is going to be 32. So we're going to say for every 1 mole of O2, we have 32.00 grams of O2. Now that we're in grams of O2, we can convert to milligrams of O2. We can say for every 1 gram of O2, that's going to be 1,000 milligrams of O2. And then we have our last conversion, which I think I'll be able to just barely fit on here, coming from our question. All right, it said 1 breath contains 18.135 milligrams of O2. So I'm going to put milligrams of O2 on bottom, and we're going to say 18.135 milligrams of O2 for every 1 breath. All right, so now we need to go through and make sure all of our units cancel. So we have milliliters of our solution per milliliters of our solution, liters of our solution, liters of our solution. Then we have moles of our C6H12O6 over moles of C6H12O6, moles of O2 over moles of O2, grams of O2 over grams of O2, and then, sorry, I miswrote that earlier. I'm sorry. This is milligrams of O2, or should have been. We have milligrams of O2. I wrote out the wrong one. All right. This should have been milligrams of O2. And this one was actually grams of O2. All right. Sorry about my mistake there. All right. Then we're going to have milligrams of O2 cancel out with milligrams of O2, and finally leaving us with breaths. All right. So now we can multiply everything on top, divide by everything on bottom. So we'll do 240.1 multiplied by 0.902, multiplied by 6, multiplied by 32, multiplied by 1,000, and then we can divide by everything on bottom. We'll divide by 1,000, and then we'll divide by 18.135. If you want to divide by the ones and multiply by the ones, you can. I'm just kind of saving myself a little bit of talking about it. All right, so we do all that math, and we get 2,292.885492 breaths. Now we want to look at significant figures. For the first number, we have 4. For the concentration, we have 4. The 0.9020 are significant. For the molar mass of oxygen, we have 4. And then for the breath conversion we were given, that would be 5. So we're going to be limited to 4 significant figures. So we're good down to the ones number, or ones digit. And so this is going to be equal to 2,293 breaths to get enough oxygen. All right, so now there's a part B as well. Determine the grams of CO2 created during this process. So this is going to be a very similar step. Basically, it's the same for all of this up until the point where we get our moles. All right, so this is where it's going to change. We're going to have 1 mole of C6H12, and then we're going to be making 6 moles of CO2, and that's where it's going to change. So this first part is going to all be the same. So I'll go through that a little bit faster. Let's go and do this in a different color. All right, so we're going to have 240.1 milliliters of our solution, and I'm going to just call it Coke at this point. We'll have 1,000 milliliters of Coke, for every 1 liter of Coke. And then for every 1 liter of Coke, we're going to have 0.9020 moles of our sugar, C6H12O6. And then for each mole of C6H12O6, we can look at our chemical equation, and I am just putting down the coefficients found in front of our sugar and then found in front of our CO2. So it just happens to be 6 again. All right, we'll have 6 moles of CO2. And since it's asking for grams of CO2, I need to convert this to grams. So I'll look at our periodic table. And when we look at carbon, we see that's 12.01. And so we'll have 1 carbon, so 12.01, plus 2 oxygens. So I have 16.00 multiplied by 2. Add all that up. And you get, for every 1 mole of CO2, we have 44.01 grams of CO2. All right, looking at our units, we'll see that we have milliliters of Coke, cancel out milliliters of Coke, liters of Coke over liters of Coke, so those cancel out moles of sugar over moles of sugar, so those cancel out moles of CO2 over moles of CO2, and we're left with grams of CO2 or grams of carbon dioxide. So we can multiply everything on top. We'll do the 240.1 multiplied by 0.902, multiplied by 6, multiplied by 44.01, and then divide by everything on bottom, just 1,000 in this case. And we get 57.1875270 grams of CO2. When we look at our significant figures, we have 4 right there, we have 4 right there, and we have 4 right there. So they're all 4, so we're going to be limited to 4 significant figures. And so when we write this out, we'll have 57.19, since the number to the right is greater than 5, we round it up. We'll have grams of CO2. All right. So hopefully that's helping you figure things out. And again, if you get stuck somewhere, again, you're trying to show me what you know. So let's say you were having a hard time trying to figure out this conversion. You didn't know how to go from milliliters to liters, but you knew you had your solution. You knew you'd eventually need to use liters to moles, and you knew everything else. That's fine. All right, well, try to make a note in your work that you know you need to go from liters to milliliters, but you have no idea what that conversion is. That's fine. Or, you know, you're very lucky in the fact that you're doing the exam on a computer, so you can actually look that up. You could Google how many liters are in a milliliter. That'd be fine. All right. But do make sure that you show your work as you're doing this stuff, so I know how to evaluate you. If you pull up some random number from online and it's incorrect, well, I don't know how you got that. So you want to tell me that you pulled it from somewhere. All right. So if you happen to look on Google and they said, all right, well, 1 liter of Coke is actually 942 milliliters of Coke. All right, well, you got that from online. Let me know that, and I'll still know that you know how to do this proper setup, even though someone was lying to you online. That happens. All right, so just make sure you show your work, and then I can give you as much credit as possible. All right, so let's go ahead and go to question number 4. All right, and I'm going to pull in something from our useful equations packet as well. Pulling up the right side of the first page, the polyatomic ions. That is the new thing I'm adding on here, kind of for convenience sake. All right, so let's read this question. You have the following chemicals at your disposal. You have copper solid, iron solid, H2O gas, platinum solid, 1 molar of copper sulfate, 1 molar iron nitrate, 1 molar chromium sulfate, 1 molar hydrochloric acid, 1 molar lithium iodide, and water. So looking at this, the question is going to ask us, without changing the concentrations, what combination of these materials will yield the voltaic cell with the highest cell potential? So we want to figure out the highest cell potential. It goes on to say, write your answer in the cell diagram. We'll go through that in a little bit, but first thing you want to do with these things is figure out what you have. So if we're looking at the copper sulfate, it says that we have a copper sulfate solution, and I want to figure out the oxidation numbers of these things. So looking at our polyatomic ions over here, we'll see that our sulfate is right down here, this SO4. And we see that we have an SO4 here, and we look at the charge, and it's -2. And so since that sulfate is a -2 charge, we would say the oxidation number for all the SO4, so the sulfur and the oxygens added together, that would be a -2 after those are added together. So that means our copper, since the overall molecule is neutral, would have to be a +2. So I'd recommend finding the oxidation numbers for, at the very least, your metals here. So we need it for copper, iron, chromium. We could do it for hydrogen and chlorine, lithium and iodine. But I highly encourage you to find your oxidation numbers. That way, when you're looking at this, you know that you're going to have copper 2+. And this will make it a lot easier when you're going through and trying to figure out which reaction or which half reaction you want to make use of. So if we look at the iron nitrate, I'm going to work this one out as well. And then for the other ones, I'll probably just write down what they are. For the iron nitrate, if we look at our NO3, when you look at our polyatomic ion sheet again, and we find NO3 right here in the middle, and that has a negative on it. So that means it's a -1 charge. So each one of our NO3s has a -1 charge. We have 2 of those. So overall, this will be a -2, taking count both NO3s. So our iron is going to have to be a +2. Now, why does this matter? Well, we know that we have iron 2+. All right. We'll talk about this in just a second. So we can do the same thing for chromium sulfate. For our chromiums, SO4 has a -2 charge. We have 3 of those, so that's going to be -6 for all of the sulfates combined. So to counteract that -6, our chromiums are going to have +6, and we have 2 of those, so each one of those is going to be a +3. Looking at HCl, that'll be +1. Chlorine will be -1. Our lithium is going to be a +1. Iodine is going to be a -1. And there we have it. So we have all those completed. So when I'm looking at, say, lithium over here, this is lithium plus. All right. So in order to find the cell with the highest cell potential, we're going to start off, since these are arranged so that we have the most positive voltage going down to the most negative voltage, we're going to start at the top looking at our reactants. Because for our overall cell potential, we want to get to the highest positive number we can. And so looking at the top reactants here, we're looking to see if we have any iron 3+. Now, when we solved for the oxidation number of this iron, it was iron 2+. So we don't actually have any iron 3+ at our disposal. So since we don't actually have this, we have to move on to the next thing. Now we can move on to I2. Now, while we do have some lithium iodide, we do not have any iodine on its own. So we can't use that. So we have to move on to the next one. The next highest one is copper 2+. And we actually do have copper 2 plus. We have copper 2 plus in the form of copper sulfate. So we have copper 2 plus. So this is going to be one of the reactions we're going to be using. Now we need to find the reaction that we're going to flip. So all these are reduction reactions. We need to find which one is going to become the oxidation reaction, because you always have to have one oxidation and one reduction reaction at least. So to find the one here, we're going to start at the bottom, because if we flip the reaction, we're going to change the sign, and when we change the sign, this would become a positive 3.05 volts. So this is going to be the highest one, if we can. So we need to look at our products, because our products will eventually become our reactants, and we need to look and see if we have any lithium solid. While we have lithium iodide, we do not have any lithium solid, so we can't use lithium solid. Then we go up one, and we see chromium solid. Well, again, we have chromium sulfate, but we don't have chromium solid, so we can't use that. Now we'll go up one more. We'll look to see if we have any iron solid. And we do. We do have iron solid right here. So this is going to be our other reaction we're going to be using. All right. So now that we know the two reactions that we need to use, we could write them out or we could flip them. I'll go ahead and flip the iron just so it's a little bit easier to follow later on. So we have iron. So our product has now become our reactant, and our reactants are going to become our products. Yields iron 2 plus 2 electrons. And then that's going to have a standard oxidation potential, so I'm going to put OX on here instead of RED for reduction. It has a standard oxidation potential. This is going to be equal to the opposite sign. All right, so the opposite sign of negative 0.44 is a positive 0.44 volts. All right, so now we need to write the cell diagram. So writing the cell diagram, what you want to do is you want to find your oxidation reaction. Whoops. We want to find our oxidation reaction. And you always want to start off with essentially the reactant for your oxidation reaction. This is what is going to be producing our electrons. Our iron is going to break up. It's going to form iron 2 plus and electrons. So it's producing electrons as it breaks up. So that's where our electrons are coming from. So we're going to say iron. Then, ideally what you want to do is you always want to make up your cells with what you're going to be producing. And in this case, we'd ideally want iron 2 plus. And the thing that has iron 2 plus in it is this iron nitrate solution. And so we're going to just write down iron nitrate. If you want to just put iron 2 plus, that's perfectly acceptable as well. Either way works. Then we need a salt bridge, so we'll draw 2 lines. And now we'll look at our reduction reaction. Looking at our reduction reaction, it's just the one written here. We're going to put our reactant first, so the thing that's consuming the electrons. So our copper 2 plus, you could just put copper 2 plus, that's perfectly fine. I'm going to put what it actually is, so we're actually drawing it from our copper sulfate solution. So I'm going to put copper SO4. Then we can put a line, and again, ideally you want to end with whatever the product is, if possible. And so we can put copper solid. Another legitimate thing you could have put here would have been like platinum or some electrode that would be inert. But again, like I said, to prevent side reactions, normally it's just safer to just put whatever your products are for each of those half reactions. All right, so that's one possible solution that you have here. Then we need to determine what our cell potential is for part A. So for our cell potential, this is just going to be normally written like that. So our standard cell potential is going to be the sum of our oxidation potential plus the reduction potential, standard reduction potential, for our two half reactions. So in this case, we'll be pulling from over here, our standard oxidation potential for our iron was positive 0.44 volts, and then the reduction potential was a positive 0.34 volts. So we'll just write those out. So we're going to have 0.44 volts, or positive 0.44 volts, plus positive 0.34 volts, and we add that together, you get a positive 0.78 volts. Now, if you add these together and you end up with a negative number, that should let you know that you probably messed up somewhere, because if it's negative, that means it's non-spontaneous. If it's positive, that means it's spontaneous and the reaction can occur. All right, the last question is saying what is being oxidized. If we're looking here, if we look at our oxidation reaction, it's whatever that reactant is. So it's asking what's being oxidized. Find the one that you flipped, look at the reactant, and we see it as iron. And so in this case, we just say it's iron, or we'd say iron solid, or iron of our iron solid, something along those lines. If we were asked what was being reduced, then we look at our reduction reaction, and it'd be whatever that reactant is. So if we were asked what's being reduced, it'd be the copper 2 plus, or we'd write it as copper 2 plus of our copper sulfate solution. All right, so that should cover question number 4. Now let's tackle question number 5. So clear that. And let me pull it up. All right, so for question number 5, we have a cell, electrochemical cell that's given to us or drawn for us, and some questions. And then I pulled these from your useful equations packet. So we have polyatomic ions, and we have our standard reduction potentials. And we're going to follow kind of a similar process what we were doing earlier. So the first question, our first part, says label the following of the voltaic cell below. We need to find the anode, cathode, direction of electrons, and direction of the sodium plus and direction of the chlorine minus. All right, so first thing we need to do is we need to figure out where our electrons are coming from, just like we did in the last question. So I would recommend looking at your solutions here, and we're going to figure out what the oxidation numbers are. So when I look at silver nitrate, looking at our polyatomic ions, we can find NO3, and that has a -1 charge. So that's going to be -1 for the NO3, and so our silver has to be a +1. Then we'll find the oxidation number of zinc. Looking at SO4, we'll see it down here on the bottom, it has a -2 charge. So that means our zinc must have a +2 charge. All right, so now we know that we're dealing with silver plus and zinc 2 plus. So now I want to look at my reactions over here, and I'm going to go down here and I'm going to find my silver plus. You can see it's right here. I'm going to mark a little line on there. All right, so we have silver plus, and then we need to find zinc 2 plus. And so if we look for zinc 2 plus, you can see it's right here. All right, and so those are our two reactions. Now, looking at these, we can see that we have a positive 0.8 volts and a negative 0.76 volts. So what we want to do is we need to combine these in such a way that we end up with a positive cell potential, or the most positive cell potential. So we need to decide which one we're going to flip. If we were to flip the silver, this would become a negative 0.8 volts, and adding that to a negative 0.76 volts, we'd end up with a negative number, meaning it would be non-spontaneous, meaning that reaction doesn't occur. But if we flip the zinc reaction, then we can change that to be zinc breaks up to form zinc 2 plus 2 electrons, and that would have a oxidation potential of now a positive 0.76 volts. All right, So now we figured out which one we flipped, and whichever one you flip is going to be your oxidation reaction. It's going to be the one that's going to be producing the electrons. So whichever one you flipped is what produces the electrons. So our zinc is going to break up into zinc 2 plus and 2 electrons. So our zinc is going to start forming zinc 2 plus. That's going to flow into this solution. And our electrons are going to flow across the wire to the other electrode. So I'm going to go ahead and draw the path of my electrons. My electrons are going to be flowing down this way. So we got the direction of our electron flow. Now we need to label the anode and cathode. All right, so the anode is where the electrons are coming from. And the cathode is where the electrons are going into. The other way you can remember it is that anode starts with an A, starts with a vowel, and this is our oxidation. So whatever is being oxidized, like zinc, that begins with a vowel as well. The O is a vowel, and so those are the same. So whatever is being oxidized is the anode. Whatever electrode is connected to the thing that's being reduced is going to be the cathode. All right, so we got our anode and cathode labeled. The cathode is this silver rod here. Now we need to figure out the direction of our sodium plus and chlorine minus. So to figure this out, our electrons are flowing this way, and easiest way is to remember that the positive charge, or the cation, is going to follow the electrons. The negative ion, or the anion, is going to go essentially where the electrons were originally coming from. Another way of thinking of this is as our silver plus is being plated onto the silver electrode, then our sodium plus has to come in and fill up that place, or fill up that gap, as our silver plus is turning into solid silver. The chlorine minus is doing something similar, where we're making extra zinc 2 plus, and that zinc 2 plus needs something to counteract with it, so the chlorine minus has to come in to play. All right, so let's go ahead and label those. Our sodium will go this way, our chlorine will go this way. So our sodium plus is going to go into the silver nitrate solution. The chlorine minus is going to go into the zinc sulfate solution. All right, so looks like we labeled everything on there. And I talked a little bit about how the silver is going to plate onto the silver electrode. And then I didn't mention this, but our zinc is going to corrode into zinc 2 plus, and as that happens, this electrode is going to get smaller and smaller or corrode away. All right, so looking at part B, what is the standard cell potential for this voltaic cell? Well, we're going to add our oxidation reaction. So we found that for zinc to be positive 0.76, and then for our silver plus 1 electron is going to give us silver solid. That's going to have a standard reduction potential of 0.80 volts. And again, I'm just pulling it from this table right here. All right, so when we write our cell potential, our standard cell potential is going to be the sum of those two. So we'll have 0.76 volts plus 0.80 volts. And when we add that together, that's going to be equal to 1.56 volts. Let's go rewrite that volt. All right, so that's our standard cell potential. And then it asks which electrode is becoming smaller. I'll go ahead and answer this in blue still. All right, which electrode is becoming smaller? This is going to be our zinc electrode. If you want to say anode, you could say anode, but in this case is our zinc electrode is becoming smaller. All right, and so that's how you go through and answer the questions. Again, I would highly encourage you to upload your work. Most students normally don't get the right answers. Some do, and hopefully you do. But a lot of times there's a little mistake made somewhere along the way, and I normally grade a lot on partial credit, as y'all have probably come to find out. So show your work, upload your work, and then I'll be able to give you partial credit. Even though most students don't get all the answers right, a lot of them get most of the points. So with that, I'd like to say good luck to you guys. And if you get stuck anywhere, I say move on to the next question, do the best you can, and then do the best you can and show as much work as you can. If you're getting stuck on, say, a stoichiometry problem, walk me through how you do stoichiometry. If all you can do is figure out molar mass, give me the molar mass. If I'm asking you oxidation numbers and you can't remember how to do oxidation numbers, give me the ones you can. Let's say you see there's oxygen there. All right, oxygen is normally going to be -2, so write -2. So just do your best and be calm and make sure you show your work and upload it. All right, with that, I'll leave y'all for today. I look forward to seeing you guys in the next video.